I think we shall start, well, we should finish chapter 4 by now, because it's only that last example, which is example 4.9 to be solved. Just to make sure, can you all see the slides? Example 4.9? Yes? No?
Yes.
Okay, great. So what do we have in this example? Here, and I will not only explain what do we have, but we will explain how it's different from previous examples, and this is very, very important. When we go through the example, here we have a boiler that is fired with a high-grade fuel oil. Now, they told us that we have a boiler, and we have that boiler is fired with a fuel oil. The idea here is that for the boiler to be operated, the boiler needs to boil the water, and that needs energy. So that's why fuel oil here is needed. Fuel oil is that when it is burned, it will give energy, and that energy will be needed for the boiler. This is the basic idea. What they say here, they say that this fuel oil, it has a standard heat of combustion of this amount. Okay. Now, remember, first of all, that the standard heat of combustion is normally taken from what? From the appendix. Yani, if I have the name of that fuel, I can get its standard heat of formation or combustion if we cannot get it from the formation. But here, because the fuel oil, they did not tell me what is it. They just said it consists of hydrocarbons. So that's why they give me the delta H ready for us. This is my delta H of combustion, which is the standard heat of that species. And that delta H at what? At 25 or 298 Kelvin. Okay, they say that that fuel oil having standard heat of combustion, it means upon burning, it gives CO2 and water as a product. And you all know that if it is complete combustion, of course, such hydrocarbon will give CO2 and water. Now, before I proceed with solving the problem, I just want to ask you, if they told me, for example, that this fuel oil is methane, then will you be able to write the reaction? Of course you will, because if it is methane, then what will you do is just writing the reaction. I'll just put it at the top, because that's not part of the question. So if it is methane, then you will put CH4 plus oxygen, because you will burn it, or combustion means burn, okay, to give CO2 and water. And then what will you do is that you will balance it. And the delta H naught for that reaction, according to what they say, is what? Is minus 40,515 joule per gram. Now, of course, if it is methane, he doesn't need, or the question that they don't need to give me the standard heat of combustion, because I can find it from appendix C4. I can get delta H formation of CO2, delta H formation of water, delta H formation of oxygen is 0, and delta H formation of CH4. And then I can balance. I can calculate delta H naught. Taban here, I did not balance it yet. I just want to elaborate on the idea if the fuel oil was given as what is it. But currently, I don't know what's that fuel. They only said it's hydrocarbon. Hydrocarbon means, hello? Are you okay? Hydrocarbon means that, okay, with the hydrocarbon means I have carbon and hydrogen, so it is CH species, but I don't know it is CH what. I will just call it C alpha H beta. Why I called it C alpha H beta? Because I don't know what is that hydrocarbon. I don't know what is it. But that's why they give me the delta H combustion. And this is one of the real example in industry. In industry, when they bring the fuel oil, don't expect that it's going to be as simple as methane or ethane or alkane or alkene. It can be complication of mixture. It can be any fuel oil that you don't know its molecular structure. But when they burn it, they found that this is the amount of heat that they get. And the amount of heat, you can see it is even in joule per gram, not in joule per mole like the table. Because the way they do it is that they put the fuel oil in mass. Like, for example, they open the container, and the container has, for example, 1,000 ton, and they burn this 1,000 ton. So then the amount of heat they produce, it's per ton or per mass. It's not per mole. So you can see how in real life, the life is not as easy as getting a table and find the value directly from there. So here is the real example where they give us a fuel, or they give us the sample as a fuel oil, and I don't know what is it. So I just wrote it here. The symbol is C alpha H beta. And upon burning it, I will get CO2 and water, but I have to balance it. Of course, just to balance, I will just remind you with the balancing. With the balance, the suggestion with the balance with hydrocarbons, I don't know if you studied that in chemistry, it's always easier to balance the carbon first, then hydrogen, then oxygen. In other words, here I have alpha carbon, then in this case I will have alpha to be written in the stoichiometric number before the C, because this is how we balance the carbon. Then hydrogen, I have beta number of hydrogen, and here I have 2. So in other words, it's beta over 2. Because if I multiply beta over 2 by 2, I will get beta hydrogen atoms. And then with regard to oxygen here oxygen, I have to put a number there to balance it. So let's see how much I have in the product. You can see in the product, I have 2 alpha of oxygen from CO2, and I have here beta over 2 of oxygen from water. In other words, I do have, I'm sorry, I'm just using a tight space because that needs to be shown later. So in other words, the oxygen in the product, it is 2 alpha plus beta over 2. 2 alpha from CO2 and beta over 2 from water. So this is the whole amount of O in the product. But here I have O2, so it's going to be same but divided by 2. Yani that here, it's going to be alpha plus beta over 4. How is this? Because I divided 2 alpha plus beta over 2, I divided it by 2. Okay, so that is basically my reaction. Okay, before I proceed, I know maybe the balance seems a bit complicated because I'm using alpha and beta. Anybody did not get this? Is that clear? If it is clear, please write clear to me so that I know that I can proceed. Again, please. Okay, اقرأ. Okay, look guys, اقرأ. I have C alpha H beta plus oxygen give me CO2 plus water. Again, why I used alpha and beta? Because I don't know what is that hydrocarbon. Now اقرأ. If this was CH4 plus O2 give me CO2 plus water. How will you balance it? You will say I have 1 carbon atoms here. It's 1 carbon atom. So here it's 1. CH4 it is 4, while here 2. So you will have to add 2 here, right? And for oxygen it was 2 here. So it's simply here you have 2, but here you have 2 there and you have 1 here. So it is 3. 3 means here you have to write 3 over 2 because you will divide it by 2. So I'm going to use the same concept exactly with that equation, my reaction. What do I mean by same concept? Means here I have C alpha, means in terms of carbon, it's alpha. I have beta of hydrogen, beta of H. It means here I have to put beta over 2, because beta over 2 times 2, it's going to be beta of H, right? And then last thing, it's oxygen. Here I have, like what we did here, we said 2 oxygen, 2 O atoms and 1 O atom. Here I have 2 alpha. And here, while there with the water, I have B over 2 of O. So if I added those 2, I will get the 2 alpha plus beta over 2. But that is the O atom. Like here, when I say 2 plus 1, it was 3, but then I took 3 divided by 2 there, right? So in other words, here, I would do the same. It's 2 alpha plus beta over 2, and that divided by 2. And that's why I wrote alpha plus beta over 4. Okay, اقرأ. Is that clear now about the balance? I cannot proceed if it's not. I can repeat furthermore. اقرأ. Is that clear? Okay, good. So if this is the case, now I'll just clear all the ink here. So what I have, I know that I have fuel oil. I know it's burning. So in other words, I can write the reaction for it. And I will show you here the reaction. Okay, just ignore all that. I'll just show you the reaction. Here is the reaction which I did. Okay, C alpha H beta, and I made the balancing as I explained in a few minutes ago. Okay, so that's up to here, all right? Now it says now that the temperature of this fuel entering the combustion chamber is 25 degrees C. In other words, when I have here I have my chamber to burn. Okay, the inlet is at 25 degrees C. So this is the given information. So I know then in my temperature scale. Okay, I know in my temperature scale that I will start with 25 degrees C. And then they say that the flue gas, of course, you know from Chinga Triple One that the flue gas means the outlet. Flue gas, it leaves at 300 degrees C. So I know the outlet temperature. So that is 25 at the inlet. And here I have 300 degrees C at the outlet. In other words, if I want to calculate delta H, it's going to be something like this. This is my delta H. But let's see what they need anyhow. So here they said it leaves at 300, and they found that the average analysis on a dry basis, wow, we are talking about the dry basis here. You remember from Chinga Triple One, dry basis mean it is OR-set analysis. It's called OR-set analysis. But even if you don't remember this, that's fine. I just want to say that based on dry basis means what? Means the outlet here, they found the composition, okay? They said they have CO2, they have CO, they have O2, they have nitrogen, okay? But upon burning that fuel, they got this as product. And those were what? Based on a dry basis means if I want to put these compositions, I will put them, but without the presence of water. And this doesn't mean that there's no water at the outlet. There is water at the outlet, but these compositions were given based on a dry basis. Now, if you remember from Chinga Triple One, whenever a dry basis was given, then we have to convert it to wet basis. Okay? But now I will show you a much easier approach. Instead of converting those and making more complication, I will just keep the composition as they are. And here 0.112, which is 11.2%, and here 0.4% means 0.004 as the composition. And the composition here, they need to say precisely whether it's mass compositions or mole compositions. But when you put the compositions here, those are based on a dry basis. So instead of converting from a dry to wet, I will just put water as an individual stream, and that would make our life much easier. No need to convert those from dry basis to wet basis. Let's keep them because they are based on having water that hasn't been counted. If it hasn't been counted, let's put it as an individual stream, and it's going to be there as individual stream. Okay, and remember that is burning, that is combustion. It means I have the fuel as inlet, and I have what? I have also burning, and burning means I should include oxygen. According to the result, I have oxygen and nitrogen as a product. It means they simply burn it with the presence of what? Of air. Okay, I will show you in the coming slide a very nice flow chart, very neat, but now here I'm just illustrating with the idea. The idea here is that we are burning the fuel in the presence of air at 25 degrees C, and we are getting a product of CO2, CO, oxygen, and nitrogen, where the compositions are given. Keep in mind that it's based on a dry basis, and we all know that according to the reaction, water is supposed to be there. That's why I put it as an outlet stream. Again, before I proceed, let me just make sure that everybody is happy with it, with the flow chart. You got the idea of it. Is that clear? If I saw clear, then I proceed. Otherwise, put your comment. Okay, wonderful. Great. Okay. All right, so if this is the case, okay, again, Bushra, I was saying here, you had doubt apparently. I was saying that I have burning, I have combustion. It means because I have burning, then the reactants that fed, it is the fuel plus either oxygen or air. And I can clearly see from the compositions given here that I have oxygen and nitrogen. So that's why the product, I put it as oxygen, nitrogen, which is the nitrogen because I have air at the inlet. And then CO, CO2, it's already given in the question. I did not change anything. But I was talking about the dry basis. Shall I convert those dry basis composition to wet basis composition? No need. Just put them as they are, because those are based on, when they did the measurement, they did not measure they use OR-set analysis for measuring. So that's why water, I put it here as individual stream. So I don't change those values. Okay? So that's basically the idea. It is fuel plus air reacted or burning the fuel to get those products. As simple as this. Bushra, is that clear? Bushra? Okay, good. Now, again, I will go back to the industry. Why they did it on a dry basis? Because this is what's happened in reality. They burn because of the temperature very high, then the water will evaporate. when they come and bring the device, they bring all the composition. They want to measure all compositions. Of course, it's without the water. I mean, the composition based on having the water evaporated. So the water has like individual streams I did. So I'm just trying to take you to the industry and see the all real cases. And then what they need here, they need calculate the fraction of heat of combustion that is transferred as heat to the boiler. And what's happening? What's happening is that when the burning takes place, there is an amount of heat, which is this, and here, this is the heat that takes place from the reaction itself. But there is an amount of heat that comes out, and they want how much this out of the maximum which is given in the question. So that is the fraction. Fraction means how much Q out of the delta H maximum. And the maximum, which is, as I said, given. So this is basically the idea. The idea they want, it's similar to the previous examples, but now here I will not only find the Q, but I will divide the Q over delta H naught 298, which is already given in the question. So let me just now show you how can we deal with. With regard to the energy balance, you need to find the Q. Q is equal to delta H because they did not mention anything related to the change in the pressure. In the question, I don't know whether it's an open or closed system, but whether it's open or closed, as long as the pressure is not changing, then Q will be equal to delta H, as simple as this. With regard to temperature scale, as we said, here I just consider that the pressure is not changing. Okay, it can be 1 bar, it can be anything, but it will not affect my calculation. And as we said, the temperature changes from 25 for the inlet product to 300 degrees C as the outlet. Okay, and because of that, we have, it is similar to example 4.7, that we have delta H298 and delta H of the product, and we have to add them together. So the idea here is exactly same as 4.7, that I have to calculate 2 delta H values. But the only tricky part here is that I don't have delta H at 298. Well, actually, I do have delta H at 298. Maybe I don't have to calculate it. But what is the problem? If you remember with 4.7, that was in joule per mole, right? So all we did, we said joule per mole, then we said 1 mole of limiting reagent reacted, because according to the given question, given information, they did not mention anything about percentage conversion. So if nothing is given about percentage conversion, then we consider that it's all converted. But the problem here is what? The problem here is I don't know the molecular weight of that species. Then how can I find it in joule? You can see this is the only difference between 4.9 and 4.7 in terms of concept. Okay, with 4.7, if you remember the procedure, we calculated delta H naught at 298, and then it was in joule per mole, then we multiply it by 1 mole. Here, do I know how many moles I have? It says joule per gram. And if it is joule per gram, then I have to multiply it by the molecular weight to get it in joule per mole. Otherwise, how can I get it? You understand the concept? So in other words, I do need to know how much alpha and how much beta to solve. Once I get alpha and beta, then I know the molecular weight, because if I know alpha and beta, then I can calculate the molecular weight. Khalas, then I would have joule per mole. Then it's going to be exactly same as 4.7. Again, I don't want to proceed if that idea is not clear. Please write again if you want me to repeat. Anyone? If it is clear, I will proceed. Clear? No again? No again. Okay, great. So if this is the case, all what I will do now is just substitute in that formula, but I cannot substitute that one in joule per mole, and then I have to multiply it by number of mole of limiting reagent reacted, which is which number of mole here, and I don't know what's the molecular weight over there, right? So as we said, we need to know the molecular weight. Now for that reason, I did this. First of all, I draw the flow chart. Now with the flow chart, you can see there that what I did, initially I just put burning. Now instead of putting 2 streams, I just put 1 stream here, which you can do with 2 streams, still fine. But what I did, I just put it as 1 in 1, and then I have the C alpha H beta, and I have the air here, which I don't know how much there. Okay, and then what I did, water, I left it in an individual stream, and there you can put it as molar composition. They have to mention then that it was molar composition, but I can put it as molar composition as they did, yani 11.2%, 0.4%, 6.2%, and 82.2%. I can do that. But if you remember from Ching 111, we were talking about choosing a basis. If none of the flow rates is given, then you have to choose a basis. And where to choose a basis? You have to choose a basis for the stream, choose the basis as the product. And this is exactly what I did. Okay. Just I don't want to forget. Is Suad with us? Suad with us now in the lecture? Suad, are you around? Okay, I think Suad, she is the one who got the highest grade in the quiz, 14 out of 15. I just would like to say thank you very much. Oh, was it Saud? Oh, I just mixed up. Sorry, highly apologize. Okay, Saud al-Dosari. All right. So thank you very much, Saud, for, yeah, I'm sorry. But yeah, I just mixed because it's only AU swabbing. Okay, Saud, well done, well done. I feel so proud of that. Indeed. Okay, back to the question. All right, so here I have the outlet, which is 100 mole, and I put it as a basis for the reason I mentioned. All you have to do now is just to apply either extant reaction method or atomic species balance to find the other number of moles. Now, what I did here, since in 4.8 we applied the Xi method, here I will apply the atomic species balance. So we'll just remind you that degree of freedom you have to count it if you want as a practice for Chenge 111. Otherwise, the problem is solvable and degree of freedom is 0. So I use extant reaction method. Excuse me, and we have here carbon, hydrogen, oxygen, and nitrogen balance. With nitrogen, whatever gets in is whatever comes out, but carbon, hydrogen, oxygen, you have to apply the atomic species balance. I will not discuss this for any reason, because that's Chenge 111. But when you apply the atomic species balance, you will be able to get number of moles of all the unknowns, and this is what I did. And something is really interesting. When you apply the atomic species balance, you will notice that with carbon and hydrogen, because what you have here basically, you have C alpha H beta. So when you do carbon balance, you will have an equation that has alpha, and when you do hydrogen balance, you will also have an equation that has beta. So you will be able to find the ratio between alpha and beta. And here, according to the atomic species balance, that is a practice for you to test your understanding of the atomic species balance. So you will notice that beta is 17 mole and alpha is 11.6. And what does this mean, simply? This simply means that my species is C11.6, H17. And can this happen in nature? Okay, of course it can. Now keep in mind that what you studied in chemistry was only alkane, alkene, alkyne. Now do we have complicated hydrocarbons? Yes, it can be. Okay, and this is called simplest form. I don't know, I think you studied this in chemistry. That is, with simplest form, you may have, this is the simplest way of getting it, but then upon multiplying both by a factor, you will get another hydrocarbon. But anyhow, this is not my story today. I only want to say that once I know the value of alpha and beta, I can calculate the molecular weight. Okay, and this will make my life easy, because now if I know alpha and beta, that delta H, I can just multiply it by the molecular weight. And if you do the math, 11.6 times 12 plus 17 times 1, which is how to calculate the molecular weight of that species, you will get the molecular weight as 156.2 gram per mole. You can see there. So what I did here, I just got this value, multiply it by this molecular weight to get delta H in joule. Or actually joule per mole, but then considering 1 mole or reacted. So that's why I have it in joule. So the idea here is just how to get this delta H, khalas. And then once I got this delta H at 298, now I have to find, because if you remember the previous slide, we said Q is equal to delta H naught at 298 plus delta H naught for the product. And for the product, I do already have the moles. So if I do have the moles of each, then I can calculate the A mixture, B mixture, C mixture, D mixture. Khalas? So that's basically the idea. But again, unfortunately, life was not that easy in life, because there is another reaction that takes place, which Smith did not mention in the question. Actually, if I would give you such a question, I should tell you from the beginning that keep in mind water liquid at, because at the outlet, the temperature was so high. If you can just see there, temperature is above 100 degrees C. Okay, it is 300 degrees C. So definitely water cannot stay in liquid phase here. So that is liquid water. So liquid water will definitely evaporate to become vapor phase. And converting water from liquid to vapor it has its own delta H naught 298, which you can get when you go to appendix C4. You will find that delta H for liquid, it has a different value from delta H formation of vapor or gas, because you are heating it up to 300. So that's why here, actually, again, if I would give you such a question, those reaction will be given clearly in the question that it's converted. But we are just assuming here that you are aware of the fact that water at 300 degrees C cannot stay as liquid phase, which you should know, actually. Another thing also, here, this reaction shows the presence of CO2 only. While you can see from the product, from the question, they said that it has CO and it has CO2. What does it mean? It means that CO2 part of it is decomposed to become CO, which is this reaction. And as I said, again, I will repeat, do not panic, because we will give you such reaction in case we give you such a question. So if we want to be detailed here, it's actually 3 reactions that took place. The one that is the burn of the fuel, the other one is the change in phase for water, the third one is the decomposition of CO2 to CO and oxygen. And because of that, my delta H here, this delta H is supposed to be the summation of those. If you can see here how to get those, you just have to go to the appendix C4 and find delta H of the reaction. And then, Doctor, why it is 8.5 here, why it is 0.4 there? If we give you the reaction, then you will find those numbers written. But here, you have to know that it is 8.5 because at the end, it is all that 8.5 H2O being converted to gas phase. And here, because I have 11 for the CO2, because here I have 11.2 for CO2 and 0.4 for CO, then that 11.6 is only 0.4 of it becomes CO. So that's why I took 0.4 of the CO2 to be converted to 0.4 CO. I know that this problem is a bit complicated, and if I want to be honest with you, this is the most difficult question in Cheng 211 from my experience, and students face problem understanding this. So I just hope that you are following with me. Okay, so let me just then raise the question. Anyone has any question before I proceed? Okay, Hamad Musa, you are asking about the atomic balance, and I would say the atomic balance is not my business. It is Cheng Triple One. You stay with yourself, do the atomic balance by your own, because I will not explain the atomic balance here. See if you can find alpha and beta. Alpha and beta is going to be like a ratio. Okay, when you solve the problem, you will find that you will have 2 equations to unknown with alpha and beta, and you can get that ratio. Okay, Muhammad? No, you were answering her question. Oh, sorry. Yeah, Aqra was saying, how can I get alpha and beta? Okay, so that is using atomic species. Yes, well done, Musa and Muhammad Musa. Yes, it is using the atomic species balance. Okay, so any other question? Yeah. So the only idea here in this example is that how to know the molecular weight of C alpha H beta, or how to know the molecular structure. Once you know the molecular structure, khalas, then you can just easily find the delta H naught. And here you can see there, this is delta H naught, the maximum delta H naught you will get. So in other words, now if I add those together, I will get the maximum delta H naught that I will get out of the process. But remember, this is my delta H naught for those reaction. Now, what I want to find the Q, which is delta H naught at 298 plus delta H naught product. Of course, as I said, the product you have no problem, since all number of moles you have all the number of moles, then you can just get CP mean. Again, the textbook method is finding CP mean for each, and then multiplying number of moles for each one of those. Yani those, and don't forget water as well, it's a product. So what he did here, he found CP mean for each one of those, then he multiplied number of mole of each. يعني 43.53 times 11.2, and then 29.93 into 0.4, and then the third one into its number of mole, and plus the one with water, because water it's 8.5. So this is what he did. In other words, it is the CP mean he did for each one of those, or he just got the CP mean of all this here. Sorry, not that. Okay, what he did here, he did the 34.69. This is for water. He multiplied by 8.5, and then for that whole one, he found the CP of the mixture for those mixture, and then multiplied by 100 mole. That is also a third option. My option that I will do is this. Look at that. I will just put the species, which are CO2, CO, O2, nitrogen, and water. And then I will put number of moles of each, yani 11.2, 0.4, 6.2, 82.2, and 8.5. That is for what? For each species. And then I will put my A, B, C, D values And then I will calculate A mixture, B mixture, C mixture, D mixture, and then I will substitute in the equation CP mean H once. What do I mean by once? Means I don't have to repeat that calculation several times. CP mean once, it means I will find the CP mean in joule per Kelvin. Once I get it in joule per Kelvin, it's just representation for all that. It replaces all this. Okay? So that CP mean, I will just need to take it and multiply it by temperature difference. And the temperature difference, you know what? It is from 300 to 25 because according to the temperature scale, we had here delta H naught 298, and here I have delta H naught for the product, and here I have the temperatures, which was 300, and here I have it at 298 or 25 degrees C. Plus, so that's basically delta H for the product. And you also have from the previous slide delta H naught at 298. So in other words, Q will be the summation of those two. Okay, and to find the fraction, it is Q over delta H naught 298 maximum. Maximum means this amount. So the idea here is simply the 5 million joule divided by 6 million joule or 6.7 million joule to get 79%. And what does this 79% means? It means that 79% of the amount of heat has been taken for the boiler or to operate the boiler or to be used for the boiler. So that's basically the idea. Okay, again, that question is, or that example is not easy and straightforward because of the absence of alpha and beta. But once you get the alpha and beta, I think everything will be clear. Now, what is most important in this chapter? You have to understand how to solve problems and how to deal with the CP mean. What is the scientific meaning behind it? Whenever you have mixture of so many species, how to get that CP mean that represents it. You can get the CP mean for each, or you can get one CP mean that represents all. Both of them, as I said, are valid, and both of them are accepted. Now, I hope this is clear for chapter 4. Any general question or specific question about chapter 4? Because as agreed, I will start the introduction of chapter 5, and on Thursday, I will answer any question related to chapter 4. So please study in the coming few days, prepare yourself. Next week you have a quiz anyhow on chapter 4. So maybe a good idea to solve the tutorial problems. And in case you have any questions, we can answer them on Thursday. It's only one example that I did not elaborate, one case that I did not elaborate. What if I have percentage conversion? And you can see in the tutorial sheet that some questions I gave were not all of the inlets being converted. But how to solve it? Exactly same, apart from the fact that with the material balance, you have to consider how to find the outlets and inlets. And I would remind you just from Chinggit 111, if you have been given, for example, percentage conversion, for example, X of A is equal to 0.2, then to find number of mole of A at the outlet, it is number of mole of A at the inlet into 1 minus the fractional conversion. That is just in case fractional conversion was given. And if it is percentage excess, also you have to know it. So that's why I said knowing the material balance from Chinggit 111 is really, really important. Okay, Mohammed Musa was having a question here. There would be CO produced and 2 reactions to be considered. You mean in that example? Yeah, in that example, we do have CO produced because it was given in the question here that I have 0.4 mole of CO. That's why when I put the reaction here, I put a reaction for the CO. I did not put 2 reactions here. So what I did, I just put the full reaction, but then the CO2 here, it's been decomposed to CO. And that's why I said in thermo, maybe a bit complicated for you, maybe. For me, I find it straightforward. But if it is complicated here, we will normally give those reactions. The blue reactions will be given to you, but for C alpha H beta here, it will be given to you as symbols. Once you found alpha and beta, then you would substitute and find the values. So that's just the only idea here. Mohammed, does this answer your question? I don't know if I get what you asked for. Mohammed, was it clear? Okay, good. So any other question? I think you need to stay some time with the material, study it, and by Thursday maybe you will come with the questions in your mind and you can ask. How does this sound? Yeah? Shall we leave your question until Thursday? Because I'm sure you would need to stay with the material more. Okay. So if this is the case, what I will do now, that will end the chapter, which is chapter 4. I put here self-suggested problems, and I put 2 tutorial sheets to work on. So I think this will keep you busy in the coming few days. Okay, so what we have in the last few minutes, I would just, or we have how many? Maybe 13 minutes or so. So I will just start with introduction on this. Okay, maybe you need to take a deep breath because we finished one chapter and now we will get into a different field. To make the link between chapter 4 and chapter 5, let me tell you this. Chapter 4 was mainly covering how the change in temperature will affect my Cp and Cv value. And accordingly, my latent heat or sensible heat will be, in terms of calculation, will be affected as well. Now, we need all this information to move from one step to another step in thermo. What we finished so far in this course, or the story so far in this course, was covering, it's supposed to be covering the whole laws of thermo. And if you remember, we covered already the 0th law of thermo. We covered the first law of thermo and we applied it on both open and closed system. And now we will move to a third step, which is covering the second law. And here I will emphasize more on how the second law is different, or what the second law will add over the first law. Okay? So, and you will notice just these 10 minutes, just introduction and making the concept clear to know the difference between chapter 4, well, first law and second law. Now, with the second law of thermodynamics, it's adding over the first law in this aspect. Number 1, energy has a quality as well as a quantity. And then, Dictora, what do you mean? Energy previously has a quality as well. Well, whatever we calculated before, we just find it out as a value. How useful is this value? We never discussed this. If you notice, I was just solving the problems with you and finding a final answer for Q, W, delta U, delta H, and so on. Here we will talk about the quality in more details, how useful it is. For example, I can tell you I have 10 kilojoule of heat that I obtained from that device. Okay, and then I have another device that gives again 10 kilojoule, but not of heat, of work. Now, in terms of quality, which one is more useful? Is the heat more useful for me, or the work is more useful for me? Although both of them are the same amount of energy, which is 10 kilojoule. You understand the idea? So here we will focus more on what is the quality of such a quantity. Okay, that's number 1. Number 2, we will talk about the direction. Now, in first law of thermodynamics, we mentioned that if the heat is added to the system is positive, the heat out of the system is negative, but that was convention. Convention means agreement to make the substitution clear for us. But do you know that some quantities? Doctor? Yes?
The slide is not changing.
Oh, really? So you mean you were unable to see chapter 5 since I started, right?
Yes.
Good news. Okay. All right, it's all right. Okay, so let me just go there because I just moved from one slide to another. Okay, all right, where is it? Chapter 5. Wow, okay. Yeah. I hope you can see it now. Yes? No? Haneen?
Yes.
We can see it.
Okay, good. And then I think I have to repeat. Okay. As we said, with the second law of thermodynamics, it's just we are continue the story of the steps. All I want to all I showed you, which you haven't seen, is this. I said step number 1 is the energy that has a quality as well as a quantity. It's not only that we have a quantity, but it's a quality. Quality, for example, the Q and W example that I just mentioned. Then we talked about the direction. Processes occur in certain direction. What do you mean by direction here? When I say direction means you have to know that if I have energy does not transfer randomly. Energy always transfer from higher to lower. يعني it's always go towards the direction of decreasing quality. Okay, which makes sense. For example, if I told you heat transfer from system A to system B, or from the system to the surrounding, the heat in that system should be higher than the one in the surrounding, so that it transferred. So that's why it always transfer in decreasing the quality. Decreasing means it will get slower. Okay, it moves from higher place to lower place of that quality. طبعا the heat is one example. Later on I will introduce something called entropy, and you will notice also it has the same concept. So the direction here is important. When I say it moves in that direction because of reason. Okay, for example, the expansion of or the work itself. Upon expansion, you know that the work will be done by the system. Okay, why it's toward decreasing the quality? Because if the system, for example, here of the work, if it expands, it will keep expanding. Okay, toward decreasing the quality, it means towards moving from high to low. But there is limitation, and here I will show you what are those limitations. Look, the direction is not reversible. يعني, for example, with the heat, if the heat is transferred from higher to lower temperature, you cannot make it transferred from lower to higher. That is not reversible. If the work is done by the system, you cannot make it done on the system unless, of course, unless you introduce a change. But by nature, it's not reversible. Okay, so there is also a theoretical limit. Theoretical limit for the performance of any engineering system. With the first law of thermodynamics, all we did is just applying the first law of thermodynamics by saying, for example, Q plus W equal to delta U, for example, or delta H if it is open system, plus change in kinetic energy plus change in potential energy. Okay, considering one inlet, one outlet. Now, the problem here is what? The problem here is when I apply the equation, I don't talk about any theoretical limit. يعني, theoretical limit means what? Means if I said heat, for example, if I said the heat transferred with an amount of 30 kilowatt. 30 kilowatt means what? Means 30 kilojoule per second. It means every second I am transferring this heat, which is 30 kilojoule per second. But there is a limit. Until when you will continue adding this heat? Here is one of the limits that first law of thermodynamics did not talk about. زين, I will give you another example. If I have, for example, again for the work, the piston. Work, if I told you here, for example, that the work done by the system is, let's say, 20 kilowatt. 20 kilowatt means what? Means minus 20 kilojoule per second, because it is by the system. Will the piston keep producing that amount of work? Well, there are limits. And we will talk about those limits. Here, second law of thermodynamics, if I will simplify it, I will say second law of thermodynamics introduces real cases, okay, and show the real scenarios of whatever that hasn't been covered in first law of thermodynamics. So that's basically. And because of that, because of those limitations, we will also discuss the degree of completion of any chemical reaction. Okay, what does this mean? It simply means that sometimes, if you have, for example, if you have chemical reaction A plus B give you C plus D. In Cheng 111, we studied that the reaction will complete if all A consumed, if the limiting reagent consumed, for example. But here also you will study from thermodynamic point of view, how can I decide that this reaction will stop? How is this? By calculating the heat and calculating, this is called degree of completion. And actually this will take us to another property, and this property called entropy. Okay? Entropy is one of the properties that when you calculate, you will tell whether the reaction proceeds or not. Yani, I don't know if you still remember chemistry. I'm just linking between courses to make things maybe clearer. But if you don't remember, then that's fine. In chemistry, you studied the entropy, and you, whenever they give you a chemical reaction, you tend to calculate the entropy change, and then you tend to say, is the reaction spontaneous or non-spontaneous? Okay, spontaneous and non-spontaneous mean the reaction is taking place or not. So here, degree of completion is simply related to entropy. Okay, but I know this slide is a bit difficult because still we did not start chapter 5 in details. But I'm trying here in this slide to summarize why second law of thermodynamics is important in terms of or compared to first law. So just to make a summary on that, I would say the quality is something that is unique with the second law. It will tell me about the quality. Okay, it will tell me about the theoretical limit. So if I would give keywords for the second law, the most important keywords are quality. The most important keywords are entropy is one of them. Entropy is one property that we will cover here. Because of talking about theoretical limits and degree of completion, those will be related to something called efficiency. And I will talk about the efficiency in details here. So, and I will talk about reversibility and irreversibility. Okay. I know we already talked about reversible and irreversible previously, but they were actually because it's related to the second law, not the first law. To be very accurate, yani. So those are the most important keywords that are related to the second law and not to the first law. So because of that, I think now we can just start the observations of the second law. What they noticed experimentally, because of the direction and because of the quality, because of those two terms, mainly they observed two things. Okay, I will mention the observations, but remember that whatever we are going to cover here is just talking about the restrictions, because in the first law of thermodynamics we did not talk about any restrictions on the directions or whatever. So that's why here with the second law we will add these restrictions. Okay, we are trying to be closer to reality, and that's why we will add those restrictions. Okay, so because of that, I have to talk about the quality and talk about the, let me just go back, talk about the quality and talk about the direction. With regards to the quality, they notice that heat and work, again, I will take you to first law and then we'll tell you how we are going to modify the second law. With the first law, we said heat and work are in one basket, correct? Now here, I will be very precise by saying, yes, they are in one basket, they are sisters, but they are different in one aspect. What is that aspect? They found that heat and work are not same in terms of quality. يعني, for example, while heat, 10 kilojoule of heat is 10 as a quantity, and 10 kilojoule of work is 10 again as a quantity, they found that work is more useful. Why more useful? Because with the heat, we normally have some loss in heat, and that's why having or producing the same quantity of work and heat, work will be more useful than the heat. You get the idea? So that's why they found that work, it is not like the heat, it's really readily transformed completely into other forms of energy. Yani the work, if you convert it to another form of energy, you can easily or completely convert it. But with the heat, that is not 100% conversion. And because this is simply because of the complexity in real life, and that complexity, I will call it in thermo irreversibility, and the loss. Loss is mainly related to the friction in processes. So that is the first observation that they noticed. Okay, so that's why we said eventually heat is a form of energy that is less useful, and because it's less useful,